Hello, everyone, and welcome to the June 2026 edition of the NOAA Drought Seminar Series. The NOAA Drought Seminar Series is a recurring monthly event dedicated to drought monitoring, prediction, and predictability. The seminar's primary objective is to establish a focused platform where national drought research, operational, and user communities can exchange the latest tools, research findings, and risk reduction activities. The seminar is organized by myself, Andy Hoyle, of NOAA Research's Physical Sciences Laboratory, Hyland Wang of the NOAA National Weather Service Weather Prediction Center, and Viva De Heza of NOAA Research's National Integrated Drought Information System, the program behind Drought.gov. Today's speaker is Dan McAvoy. Dan is an associate research professor at Desert Research Institute and regional climatologist at Western Regional Climate Center, where his primary focus is drought, snowpack, and mountain hydroclimate dynamics in the Western United States. The Western Regional Climate Center is one of 6 NOAA-funded centers across the U.S. His work for the WRCC includes climate services, communication and outreach, and oversight and development of use-inspired web tools to access and visualize climate data. Dan joins us to present ways in which snow droughts are defined, the role of warming temperatures on snow droughts, atmospheric drivers, and ongoing efforts to communicate real-time snow drought conditions and impacts to the water resources community. Thank you for joining us, Dan, and please begin.
Thanks, Andy. Let me get my slides up here, and we'll jump right in. Well, first, I'd just like to say thanks to Andy for the opportunity to be presenting on this webinar series today. It's really exciting, and looking forward to telling everyone a lot about snow drought today. So I think probably most people on the call are pretty well aware that there was a snow drought that occurred in the Western US this year. There was a ton of media on this event that unfolded throughout the course of the winter and into the spring, and we saw news headlines, and these weren't limited to Western US news outlets. This was coast to coast, the New York Times, the Washington Post, and then to the West Coast, we had headlines like this talking about the historic snow drought, unprecedented, that word came up a lot, and things related to water supply. But then we also had a few headlines like this one, which on the bottom left, talking about not just record dryness, but also flooding. And I actually really like the subtitle on that bottom left headline, talking about the nearly snowless winter wasn't the same everywhere. And so that's one of the things I'm going to touch on is how snow droughts can be very different spatially, even within one season. And we saw that this year. So what is a snow drought? That's, well, one of the main things I'm going to cover today. It is a relatively new term in terms of the last decade or so of being used. And we'll talk about sort of the origins of the terminology and the definitions. But there's one really simple key that is required for a snow drought, and that's having a deficit in the snowpack. And to describe the snowpack, I'll be talking about a lot today, the snow water equivalent, or the SWE, which is the amount of water that's stored in the snowpack, and that's a critical variable to understand the snow and also water supply in the Western US. And this map over here on the left is from the NRCS SNOTEL network. I'll talk more about that, but this is showing basin averaged. All those polygons are river basins, basin average snow water equivalent percent of median on April 1st this year. That's the time around when the snowpack peaks in the Western US. And this map does not look very good. It's mostly red, and so anything in red is less than 50% of median. There are a few areas that are a little bit above that, but there aren't any areas that are above 100% of median. And so I'll be sprinkling in some information about this year's event throughout the course of this talk, but really I'm going to spend a lot of time on the science, understanding what snow droughts are and how to define them, and then get into the data, applications, and impacts around snow droughts. So as I mentioned, this term snow drought really is relatively new in longer term thinking of climate and hydrology. And it really didn't start showing up until around 2015. And that was another really bad snow drought. year. And it turns out it actually had a lot of similarities to what we saw this year in some ways. And at that time in 2015, that type of event had not really been seen in the analogs that we had for weather and climate records. And so again, this is that snow water equivalent map, but this is for April 1st, 2015. Really bad conditions in the Sierra Nevada, Cascades, into the Great Basin and Rockies. And there was a study that reconstructed snowpack in California, showing it was the lowest in the past 500 years. So a really extreme event. But what was different and what really hadn't been seen up until that year was the fact that it wasn't necessarily dry everywhere. And so this is a similar map on the right, but now this is showing the October through March total precipitation as a percentage of normal. And what we see here in places like the Cascades in Oregon and Washington, where you had snowpack at April 1 at less than 20% of median, the precipitation was close to average. It was dry in the Sierra Nevada and other places, but we had this case where low precipitation was not the primary driver of this snow drought in much of the Pacific Northwest. So what was driving that snow drought? It was the incredible warmth that we had that year. Again, similarities to this year. This is a map showing the October through March temperature percentiles from that 2015 year. Record in some cases along the West Coast. And so, it wasn't just a low snowpack. Snow droughts can be more than just a lack of snowpack, and they can also have above average precipitation in some cases. And it was really this 2017 publication by Harpold et al., a short communication piece that really brought up this idea that there's a need to define different types of snow droughts. And they highlighted the fact that there was low snow up and down the West Coast, but what they called it a warm snow drought in the Pacific Northwest, where precipitation was near or above average in some cases. Stream flows were low, but they weren't extreme. And then a dry snow drought in the Sierra Nevada, where the precipitation was really low, and that drove most of the low snowpack that year. And so these were really the two basic definitions that began how snow droughts were initially defined. Interestingly, these two definitions didn't explicitly use temperature even to describe the warm snow droughts. So again, just to reinforce these basic original definitions for snow droughts, the dry snow drought is the result of meteorological drought. So low precipitation leads to low snowpack. And then the warm snow drought is a result of warm temperatures and not necessarily a meteorological drought, although it could be both, as we'll see as we go through this talk. And really, we're starting to see more and more of these warm snow droughts, and some of them are quite wet. And those impacts are really less understood, I think, and they can be a lot more difficult to communicate, as we saw this year in certain locations. I worked on a study with Ben Hatchett not long after that 2017 Harpold paper came out to really kind of look at the origins of snow droughts in the Sierra Nevada. And we developed this really simple quadrant framework to be able to throw up a whole bunch of years or different stations or different locations and classify them as a dry snow drought on the bottom left or warm snow drought on the bottom right. So this is using snow course observations, a snow water equivalent on the vertical axis, and then again that October through March precipitation on the horizontal axis. And so again, we didn't use temperature in this situation. We just used that basic definition of a warm snow drought has near or above average precipitation. And of course, it has to have this below median SWE. That dotted line is 80% of median. That was sort of arbitrary that we chose there. And then on the left was the dry snow drought, where you had below median precipitation and below median snowpack. And so we saw 2015 fell really into that dry snow drought for the Sierra Nevada, but it was extremely warm that year as well. And then we had 1977, that was the really dry year, and these bright blue dots and some other events on the right there. So again, this was a basic framework to be able to visualize and classify snow droughts relatively simply. And I'm really going to drive home this point about warming temperatures having really big impacts on snow droughts, and especially this year, we really saw that. And so this graphic here is from a tool called the Climate Reanalyzer. It has some really great graphics, and you can get these time series really quickly. And so what this is showing is the wintertime freezing levels, December, January, February, going back to 1940 using reanalysis data, averaged over the Western US domain. And so the freezing level is the level in the atmosphere at 0 degrees Celsius or 32 degrees Fahrenheit. It's a very rough proxy for snow level. The snow level is likely somewhere within a few hundred meters of that, but it can tell you a lot about the rain snow line and where snow or rain is falling. And we see a pretty clear trend upward in this freezing level. And these are standard deviations that are plotted on the y-axis of the freezing levels using the 1991 to 2020 baseline. And so we have been seeing this trend of upward freezing levels. And then 2026 was basically off the charts in terms of positive anomalies there, almost 4 standard deviations. And before that, there hadn't been any other years above 3 standard deviations. And mind you, this was December, January, February, before the intense March heat wave that I will get into a bit later. So when you have these higher freezing levels during winter storms, you can get more rain in higher elevations into the mountains. We saw that this year. You can have rain on snow, and so that can melt the snowpack, and it can also ripen the snowpack and get it ready to melt quicker. And then during dry periods in the middle of the winter, when you have sunny, dry conditions, you can have really slow melt at high elevations, and you can have melt at lower elevations too. And then in the spring, you can really have this rapid snow melt during spring heat waves, which we also saw this year. So there's a lot of ways warm temperatures can really drive snow droughts into snow drought or make them more severe than they already are. So continuing on this theme of defining snow droughts, there's actually a lot of ways that snow droughts are defined in the literature. There isn't an agreed upon best method. This is a figure from a 2023 paper, a Heldmeyer et al. Paper. So the center panel there is this framework developed that I showed you earlier with the 4 quadrants, dry snow drought on the bottom left, warm snow drought on the bottom right. In the paper that was being written, their method is on the left, and then there was a 2019 paper on the right. And the point of this slide is that if you look at, these are all using different methods to classify snow droughts. The one on the left is actually using the ratio of snow water equivalent to precipitation, which can indirectly get at the temperature impacts. The one in the middle is using the April 1st SWE anomaly. The one on the right actually does use a temperature metric, which I'll get into, thawing days, which is accumulating the number of above freezing days throughout the winter. And on the bottom, there's various forms of precipitation being used. And the point here is that for all these dots are the same events for all 3 of these panels, and they all come up with different warm, different dry, different warm and dry instances of snow drought. So it doesn't matter how you define it, you're going to get different answers. And it really depends on who you ask and what you're doing with the data in terms of how snow droughts are being defined. So I really, again, want to make this point that snow drought is a multivariate problem. It's more than just looking if the snowpack is above or below average. You need the SWE, but you also need the precipitation, and you really need that temperature for a robust classification of snow droughts. And on the previous graph, I showed that panel on the right where they used thawing days. And so there's been, that 2019 paper was really the first one that I could think of that used this used 3 conditions to define these snow droughts using all 3 variables, temperature, SWE, and precipitation. So for example, with the dry snow drought, you have to have below normal SWE, below normal precipitation, and below normal thawing days. And then the warm and dry is below normal SWE, below normal P, but above normal precipitation. And so there's been quite a bit of work since then. And these are all relatively new papers that are starting to use different variations or flavors in this conditional method to define these snow droughts that includes temperature and includes precipitation and SWE. This Hammond paper used seasonal mean temperature instead of thawing days. It used March average SWE and October to March precipitation. And then this 2024 paper, again, they used seasonal mean temperature. They used a different SWE metric. They used accumulated SWE increases. And something important here that I want to touch on is that they didn't just look at April 1 or peak SWE. They looked at early, mid, and late season. And there's an argument to be made that we should be looking at snow drought evolution throughout the course of the season and not just retrospectively looking at, say, peak SWE or April 1 SWE. So another thing to touch on here is that all these methods use SWE below the mean, which arguably is not necessarily a snow drought. A drought should be an extreme event. And so if you have something that's just below average, is that really a drought? I would argue that it's not, and there should be some more stringent threshold, like a percentile basis or something like that. But these are all three commonly used methods that use this multivariate criteria. And so again, getting at this point that April 1 SWE or even peak SWE doesn't tell the whole story. I did some work with a few others with this idea of tracking snow drought throughout the season as daily changes. So again, on the left, we have this quadrant system with dry on the bottom right, warm on the bottom left, warm on the bottom right, but also using percentiles, precipitation percentiles, US drought monitor classifications to try to better integrate it into drought monitoring. And each dot there is a daily value from November through December. And you can see that in this particular case, the snow drought moves from no snow drought into a warm snow drought into a dry snow drought and then back into a warm snow drought. And really there are implications and impacts from being in these different types of snow droughts throughout the season. And this explainer on the right kind of tells you about that. We do have a tool available where you can look at some of these in real time at Huck 6 River Basin scale from SNOTEL data, and that link is on the bottom right. And so further getting into that point that you need to look beyond just April 1 or peak SWE, we can talk about spring heat waves and those impacts on snow drought. Again, the timing is very important to understand here. And so, and we saw a very intense spring heat wave this season. And so this study that I worked on here used a case study from 2021, April 2021. There was a series of several heat waves that moved through the western US. They caused record snowmelt in some cases based on the SNOTEL stations. There were various patterns of high pressure parked over the region that was the driver of this snowmelt. And the big thing to point out here is that the snow drought really intensified during the melt season after April 1st. And so the plot on the right is showing the large river basin April 1 SWE percent of median between April 1st and May 1st. And let's say you just look at the California region, for example. On April 1st, it was below average. It was 80% of median. But then by May 1st, it was less than 40% of median due to this spring heat wave and rapid snowmelt. So again, this was something that occurred after the peak, after April 1. But it was critical to understanding the seasonal evolution of the snowpack and water supply inevitably. So going a little bit further with these spring heat waves, Alan Rhodes from Morris Berkeley National Lab led a study that was just accepted into Science Advances last week and will hopefully be in print soon, about what he has termed snow eater heat waves. And so that's similar to what I showed on the previous slide. The idea here was to go beyond just the case study and go back in our history and try to characterize these spring heat waves or snow eater heat waves as they're termed in this paper. How often do they occur? What are the magnitudes? How can we define them? In this case, the definition was only based on 2 meter surface temperatures. And you had to have a very strong temperature anomaly lasting more than 3 days. And a key thing is having above freezing air temperatures. the entire time to classify these snow eater heat waves. And that was tested in an operational snowmelt model to see how well those models did, and if adding information about the heat wave as it evolves can improve those models. And so really one of the key findings of this study was that on these snow eater heat wave days compared to all days, you saw about double the rates of snow melt compared to regular days. So we did see big increases in how fast the snow was melting. Interestingly, these events were also linked to 7 of 11 superfloods, where you had 1983 was an example where you had a ton of snow left in the mountains after a really big snow year that led to flooding. And so you can have these events, again, cause snow drought, intensify snow drought, but also cause flooding. And so the next phase of that project then, so I mentioned we only looked at the 2-meter temperatures really in that study, is now to look into the atmosphere and see what are the synoptic weather patterns associated with those snow eater heat wave events. And so we're working on that right now, and in the middle of that study, basically using the catalog of events that was defined in the Rhodes paper. There were 55 events. Several hundred days total, as some of these events lasted a few days, some of them lasted 7 to 10 days or longer. And so really understanding what are the atmospheric drivers of these events, and can understanding these atmospheric patterns help predict the events at weather and subseasonal timescales. And the plot here on the left is showing the 500 millibar geopotential height anomaly, where basically the patterns of high and low pressure in the middle of the atmosphere. And when you take the mean over all these, we see a very large area of high pressure over the western US, which is not all that surprising because heat waves tend to be associated with high pressure. But when you start digging into it, there are definitely variations in those ridging patterns from different over different events, and even within events, you see variations. And so what we want to do is then kind of break this down and see if there are dominant patterns or modes of circulation in the atmosphere that lead to these snow eater heat waves. And so these are some initial results from a cluster analysis to see if we can see distinct clusters of high pressure areas over the western US driving these heat wave events. And the initial result does show quite a bit of variation in where the ridge is and where the area of low pressure is. That's often further off into the west coast. We want to look at other variables next outside of just the 500 millibar heights. Definitely I want to look at some wind speed, but also some precipitation or water vapor variables, because I get the sense that with some of these patterns, you don't have that ridge just parked over the western US, and there could be interesting things related to atmospheric rivers, potentially rain on snow, wet versus dry days, and then also analyzing the patterns of SWE and snow melt associated with these varying clusters. So this is a work in progress, and I look forward to down the road, hopefully having more to share on this project. So I'm going to shift gears a little now and get into talking more about the data. Of course, we really need to care and learn and understand the data for all of this snow drought research, monitoring, and also the applications associated with it, what I'll talk about after this. So we have in situ or point observations. I already talked about the SNOTEL network. We also have snow courses. We have various gridded products. We have observation-based data sets. We have model data from snow models or land surface models, remote sensing. And let's not forget that we don't need just the snow data. We really need that temperature and precipitation data too for good analysis and work on snow droughts. And so I want to start with the in situ observations, the SNOTEL and snow courses. These are invaluable, and we're so lucky to have this network in the Western United States. So the SNOTELs are shown on the left there. These are automated snow pillows, and many of them started around the year 1980, collecting snow water equivalent precipitation and air temperature, and a lot of them have soil moisture as well now. And then we also have snow courses, which are the manual observations that have been going on since a lot of the sites have data going back to the early 1900s. And so these two data sets combined have really been crucial to our understanding of snow drought in the Western US. But there are some limitations and challenges associated with these data sets as well. Between the two data sets, well, let me backtrack for a second. This graphic here, this time series graphic, is from a recent report put out by the Western Water Assessment. And this is showing the snow course data. And these time series go back to 1941. And so, the point here is that you get a lot bigger of a sample, a longer time series, and more context in terms of things like records like this year when assessing record low snowpack. But they do have different sampling. The snow courses are monthly, the snow tells are daily. They have different periods of record. And, a big challenge here is that these observations are primarily at the middle elevations and the mountain areas that really collect a lot of snow and are critical for water supply, which is really great. And that was their purpose, was to be put there for water supply forecasting. But we're missing out on a lot of the low elevation areas in the basin, as well as the highest peaks. Think about those ridges and peaks that hold snow late into the summer. And so we don't get that story of the full basin, and that's where we need some of these gridded products. But both of these were incredibly useful this year, but it did introduce some confusion when talking about record low snowpack. And so we had to be very specific and say whether we were talking about the snowtel record that began in 1980 or the snow course record that began in 1941, or some of them went even further back than that. And then the gridded products, there's really a lot of potential to use gridded snow water equivalent along with temperature and precip. But we have several gridded SWE products out there that are updated in real time or near real time. One of them is SNODAS, which is an operational 1 kilometer spatial resolution product. You can view that on a tool called Climate Engine, where you can look at the percent of average, percent of median. You can look at the percentiles and map them and get time series. And then on the bottom left is a product from the University of Arizona, where they have a 4 kilometer SWE product. Again, you can map it and look at anomalies and percentiles, which is a great start. And then on the upper right here, we have some information from the Montana Climate Office, where they have a drought dashboard, and they went a step further and created some of these standardized snow water equivalent maps and products that can help integrate more into operational drought monitoring. They've even developed some of these tools to look at the hypsometry of a basin, kind of showing how much snow is available at different elevations based on the gridded SWE. And so these are all incredibly useful tools to look at the SWE and understand, historically where you are in terms of amount of snowpack. But what really is still lacking, and I think that we really need to start working more on, is developing some of these tools that integrate SWE temperature and precipitation into an index or a product where you can quickly characterize these different flavors of snow drought that I was talking about earlier when we were talking about definitions. And then there's other spatial products that really have a lot of potential to be incorporated into snow drought monitoring. There's satellite remote sensing products. So on the left here, we have the snow covered area product from Snow Today, from NSIDC. This was an incredibly valuable tool this year. And so this maps the fractional snow covered area. And so not the snow water equivalent, but it doesn't tell you about the amount of water in the snowpack, but it does tell you where there is and isn't snow, which is something different from the snow water equivalent, and does get you a little bit closer to telling that full basin story at higher and lower elevations about just how much snow is on the ground compared to average. And then on the bottom right, I think many folks may have heard of the Airborne Snow Observatory. They do airborne LiDAR flights and have super high resolution snow water equivalent mapping at at basin scales, at select basins where they're able to do these flights. I believe it's 50-meter spatial resolution, so incredibly high resolution, a ton of detail. These are some example maps from their website. And we need to start thinking about how to integrate products like this into snow drought monitoring. These, like the airborne observatories are a bit more challenging because they're not flown frequently. They're flown a few times a year. And only over select basins, but there are some areas that are starting to get a time series of data from the Airborne Snow Observatory. And so how can this data add value to our understanding of snow drought years for situational awareness, even from years like this year that we had? And so we should start thinking about that type of integration of these products. Okay, now into the application. So why do we even care about the definition? Is it really just an academic exercise, or are there reasons to have all these different definitions? Well, I think the definitions do matter for a number of different reasons. And so one of these is for outreach and communication and real-time reporting. And this is a product that I've been working on now for a number of years that I wanted to highlight as an application. This is some screenshots from the NIDIS, National Integrated Drought Information System, the snow drought updates that we put out, myself and the communications team at NIDIS and others, once a month from about December through June every year, to basically take a snapshot of the current snow drought conditions and try to distill it down into a short report that's accessible and understandable by many types of users. And so this is one place where we really could use a better snow drought definition. This year was challenging. We were able to describe the state of the snowpack quite well, thanks to SnowTel and some of these other gridded products. But it was very challenging to talk about warm snow drought or dry snow drought, warm and wet, in our reporting, because we didn't have those multivariate indices or summaries at our fingertips. And so that's where these kind of definitions with different approaches can really come into play if we have it at our fingertips in a real-time sense, which we don't really have yet. And so we need this faster access to the specific snow drought types. And I also just want to highlight on those snow drought updates that they're hugely collaborative. So I just mentioned the folks who write them each month, and then we send them out to this long list of partners to try to get feedback from regional and local experts, because we're not able to cover all the details. These reports cover the entire Western United States and Alaska. And so we have lots of federal partners, some private partners, airborne snow observatories, universities, all contribute and come into this document and share their perspectives. And it really improves the reports that come out each month. So more on the applications. So how can we integrate snow drought into operational drought monitoring systems like the US Drought Monitor that I think most are familiar with? This is the most recent drought monitor map shown on the left. As I mentioned, percentiles are really commonly used to standardize inputs into the US Drought Monitor. And I think having, again, an index or a classification system that can easily integrate into the workflow of operational drought monitoring systems is something that is still lacking to some extent and can really add value if some more work was done in that space. And then forecasting and predictability. That's another reason why we need to have a good definition to use. If we want to forecast the snow drought, we need to be able to define what exactly it is we're forecasting. And so there's not a lot of forecasting of snow water equivalent or really snowpack throughout the snow season. It's incredibly difficult to accurately predict at long lead times. But there are a lot of forecasts and outlooks that provide the drivers of these snow droughts, including temperature and precipitation. And so I think it's sort of untapped right now in terms of understanding how well we can predict snow droughts at these weather and then subseasonal to seasonal timescales. But then on the flip side of that, we can think about, can we use the snow drought as an initial condition as a predictor of summer drought? And there has been some work showing that, yes, including the snow drought characteristics in summer drought forecasts, in addition to precipitation and temperature, can add some value and improve the skill of summer drought forecasts. And so this is an area, the forecasting, and not just the forecasting, but the predictability, the large scale climate drivers of snow droughts. This is an area that there has not been a ton of work done yet. And I think there's a lot of room to grow in this area. And so getting into the impacts now. I think the most obvious impact to most when we think about snow drought is water supply or low water supply. And I always love to show again, so this on the left is Dr. James Church, who developed the federal snow sampler that is used in the snow surveys. I mentioned that snow survey data that goes back to the early 1900s. And I really love these old pictures just showing, and new pictures showing that the same method is still being used today to sample the snowpack. And so it's been linked, this is why the snow survey was developed, because we knew there was a link even back in the early 1900s between low snow and drought and low water supply, like low reservoirs shown on the bottom right and low stream flows. But it's more complicated than that for the hydrologic impacts. There's several pretty recent studies here. Again, this is an area that's pretty new in terms of the research in really understanding the regional and local impacts of snow droughts on water supply, because it can vary greatly. And, in general, when you have this dry snow drought that's driven by low precipitation, we expect lower stream flows. But the situation that gets a bit more interesting and more challenging are these warm snow droughts, and the response to stream flow can be varied. There's some papers showing that the type of hydroclimate depends on whether you have above or below average stream flow during a warm snow drought. There's other studies that are showing the size of the catchment matters, whether you have more or less stream flow during these warm snow droughts. And so it's not as cut and dry as snow drought equals low water supply. And we saw that this year. And it was quite interesting to see it unfold differently in various places. And so these are a couple examples now. So on the right, data from the SNOWTEL network. On the top is the SWE time series. In the middle is accumulated precipitation. And on the bottom is air temperature. And then on the left is runoff at one of the gauges in the headwaters of this Truckee River Basin. And so what we saw here was a warm and wet snow drought. And this is based on those classifications I showed earlier. We had second lowest SWE on record, warmest temperatures on record, but precipitation was at the 60th percentile. So this was certainly a wet and warm snow drought. But it did not result initially in hydrologic drought. So on the left, we have the one in the box there is this water year starting in October, showing the daily discharge. And it was above average for a lot of the year because we had warm and wet storms in December, and then it definitely petered out as we got into the spring. But when you look at the accumulation over the year, it's close to the 75th percentile right now. And even if that flatlined through the rest of the water year, we'd be at average runoff for the season during this second lowest snowpack on record. And also the impact of that heat wave. You can really see the snowpack tanking. It was a dry period, and we had these warmest temperatures on record during that period. So this is the same slide, but a different region now. This is in southwest Colorado, looking at the Gunnison River Basin, a much different hydroclimate than the Sierra Nevada. And in this case, it was a warm and dry snow drought. It was the lowest April 1st SWE on record. But the precipitation from October through April was at the 16th percentile, much drier than in the Sierra Nevada. And the temperatures were extremely warm all year at the 100th percentile. And one thing to note here is the hydroclimate is very different. The winter flows tend to be the lowest in the year, whereas in the Sierra Nevada, you can have these flashy midwinter flows. And the winter flows weren't too far from average, and it wasn't until spring where we really start to see the runoff really tank. And if you look at accumulated runoff now, it's below the 25th percentile and likely to get quite a bit lower, as the forecasts are indicating really poor warm season runoff forecasts. And again, the heat wave impacted the entire western United States, and including southwest Colorado. We have recreational impacts. This is a big one. I'm a skier. There's a lot of skiers and snowboarders probably on the call, and so these are some headlines. This was from earlier in the season, but there was a lot of impacts to ski areas, closing resorts in Oregon. Huge bummer in Oregon, as resorts had to close due to rain-soaked slopes. Large corporations like Vail were complaining on skier visits being down due to lack of snow. And so this was impacting both the snow enthusiasts and also the local economies, as well as major corporations like Vail. And then fire danger is the last impact I want to talk about. This one is not a one-to-one relationship. It's very complicated with fire, but there are some things we can point to, like in snow drought years, we often have earlier snow disappearance dates, so the snow melts off quicker. And what that will do is reduce the summer soil moisture and oftentimes lead to earlier starts to the fire season. On the right is a map of the GRACE soil moisture from late March 2021, which turned out to be a really bad fire season for the West Coast in California. But there's a lot that happens in between when the snow melts and when fire season begins. And we even saw that this year, where we had some cooler and wetter patterns in April and May. And that can dampen some of the effects of the snow drought. And so again, I think there's more work that needs to be done, really connecting the timing and various types of snow drought to fire danger conditions. Okay, to wrap up, I want to come back to conditions this year. So again, we know the snowpack was really bad. It was a bad snow drought. How bad? Well, a whole bunch of states. Arizona, I have them listed out here on the right, saw the record lowest snowpack on April 1st based on those SNOTEL records. And it was an unprecedented snow drought in some cases, even going back to the early 1900s, looking at the snow course data. And we had several different flavors of snow drought emerge this year. We had the warm and wet in the Sierra Nevada and places like Washington, Northern Rockies, and then other places like Colorado, Oregon, into the Great Basin, where it was a warm and dry snow drought. But the one thing that stood out everywhere was the warmer temperatures were really a driver everywhere. This is a map showing the October through April temperature rankings from NCEI. These darkest reds are the record warmest. So almost every Western state except for Oregon and Idaho, that were second warmest, and then Washington, that was the fourth warmest. So again, it's really, really critical to incorporate temperature into these snow drought analysis and classifications. We had the March heat wave. This is a slide made by the National Weather Service Reno office that was highlighting the event. Temperatures in the 90s and hundreds in March, unprecedented temperature values. Reno had temperatures that were closer to June temperatures. Their March temperature was almost the hottest. Their average March temperature was almost the hottest April on record. That's how warm it was. And they compared this to the 2021 event that we looked at in our case study with the rapid snow melt. And so this seemed like a snow eater heat wave. We didn't do the analysis on this event yet, but it will likely wind up in that classification. And so we lost snow early, pretty much everywhere in the Western US. These are a couple of photographs that I took from Mount Rose ski area. The base of this ski area is high for the Sierra, for the Lake Tahoe area at 8,200 feet. And in late March, we had patches of dirt showing on the runs. And then in mid-April, when they were closing, I've never seen this much bare ground, even on closing date. This is high elevation, and it tends to hold a lot of snow. So lost snow really early. But the hydrologic responses during the winter and early spring were different. This map on the right shows reservoir levels across the western US. And they're not all red and they're not all flagged. The big ones in the Colorado River Basin are in very bad shape. But as you go into California and into the Pacific Northwest, that's not necessarily the case because of storage in these reservoirs and also seeing rain during the winter coming in and filling these reservoirs as well. But pretty much universally across the western US, the warm season water supply forecasts are looking very poor. A lot less water than usual coming out of the mountains into the streams and reservoirs during the warm season. And this is also the time where we have the highest demand for water from people and also the highest demand from water from the atmosphere. And so again, these somewhat complicated hydrologic responses and impacts we're seeing this year. And so just a few key points here to end. You need that low snowpack to have the snow drought, but that alone is certainly not telling the whole story. You need these other variables of temperature and precipitation, and the warming temperatures are really becoming an important driver of these snow droughts. And finally, those hydrologic impacts can really vary, and so it's not safe to say just because you have a snow drought that you have low water supply in the winter and spring or even summer. And I think there needs to be a lot more work done on regional and local impacts of snow droughts to water supply systems. And I want to end with a quote from a paper from the great Kelly Redmond. He wrote this depiction of drought, a commentary in the Bulletin of the American Meteorological Society about really how challenging it is to describe drought. And so it's not likely that there's an easy way out of this depiction dilemma. Drought is a many-headed creature, and its full description requires an equally diverse menagerie of indices and indicators. And so I really think snow drought has now added another head to this creature. But it's important because now we're really, again, starting to understand more aspects of not just snow drought, but drought as a whole. And I will stop there. And thank you all for attending and listening today, and see if we have any questions to answer.
Thank you so much, Dan. What a fantastic presentation, and timely too. So Hyland is going to come on in and moderate the Q&A, and there are many questions for you.
Okay, thanks, Andy, and thank you again, Dan, for the excellent presentation. I'm Helen Wang from Weather Prediction Center at NOAA. So next, I'm just going to moderate the Q&A session. So here we have a number of questions already. The first question, when using low precipitation in the definition of dry snow drought, does that include precipitation as both rain and snow?
Yes, it does. So the precipitation in those snow drought definitions are not splitting it up into phase. So that's looking at seasonal totals of just liquid precipitation and not distinguishing phase. But that's another aspect of snow drought that's challenging and needs more work to understand, again, freezing levels and precipitation phase.
Okay, thank you. So here's the second one from the same audience. The same way that simply looking at below median to classify as snow drought, how does the changing period of baseline impact how to classify retroactively the seasons? One can argue that more recent periods would indicate lower medians than longer periods or using previous periods. I think this question just is regarding the sensitivity of identification of snow drought and snow drought season to climatological baseline period.
Yeah, that's a good question. I think that's like really any other type of drought monitoring or climate study or application. The choice of the base period does matter because you'll get different answers in terms of how severe an event was, or if it was a record or not a record. And so most of the studies that I've worked on and that I've seen tend to use the more modern baseline period, try to use that 1991 to 2020 period if it's available. But then again, getting back to using the snow course data that has data going back to the early 1900s, we were using different periods of record. So we were having different rankings and different percentiles. It's definitely something that should be taken into consideration. And I think you will get different answers depending on what base period that you use.
Thank you. So how to determine if snow eater heat waves lead to sublimation versus melting or flooding? Because sublimation causes the permanent loss of water, but melting causes flood or have the potential for capturing that water.
Yeah, great question. We did not consider sublimation in that study. We were just looking at melt potential from the Snow 17 model, and then also just delta SWE from the SNOTEL stations. And so that is a uncertainty for sure in that study is how to account for sublimation. We did not get to the level of being able to have model outputs in that study to include sublimation.
Okay, great, thanks. So next question, is snow drought classification always a retroactive action? When in the water year is appropriate to start saying that we are in a snow drought?
That's a really great question. And the argument that I make is that it should start right from the beginning of the season, to see how it progresses throughout the season. It's tricky to look at snow water equivalent anomalies, for example, really early in the season or really late in the season when you have the magnitudes of the amount of snow water equivalent are really low. So you need to have some thresholds on how much snow is actually on the ground. But there are different impacts from early season snow droughts to midwinter snow droughts to the late season snow droughts. And so there are some studies now that are not just using peak SWE or April 1, but starting to look at early, mid, and late season. See how the classifications change, but also see if there's impacts that are different between those time periods.
Okay, great, thanks. So here's a comment. I 100% agree that a good definition of snow drought is needed. I use the summaries and narratives, and sometimes it is hard to explain to water resource managers what snow drought means when the cumulative precipitation as rain is larger than normal. Just feel free if you have any comments. Otherwise, I'll go to the next question.
That's an excellent comment, and I fully agree.
Thank you. So next question. I saw that the mountains in Southern California, for example, San Bernardinos, etc., were not included in the initial snow drought figures. Can you explain why? Thank you.
Yeah, so the mountains of Southern California and other places around the West, those do not have reliable long-term observations of snow water equivalent. So there's no SNOTEL stations in San Bernardino Mountains, for example. There may be a few snow courses. And so in places like that, that's where you have to rely on gridded model outputs, reanalysis model outputs, snow models, things like snow-covered area, because there are no SNOTEL stations in those mountains. And so that's a really good question. We don't have, again, with SNOTEL, we don't have them everywhere. And so we're missing the story in some places, and we're missing any observation at all in certain places like Southern California.
Thanks. Thank you for the presentation. How can we start to think about health impacts might be different during different types of snow drought? How might snow drought in one area impact health in another area that relies on water from the mountainous region? Thank you.
That one I'm not sure I have a great answer for. I am not really aware all that much of health impacts. That's one I'd have to think about, and I just don't have a good answer for right now.
Yeah, no problem. So here we also have a few questions. So the presentation is mostly on snow drought types and monitoring. I wonder if you could comment a little bit more on the predictability of snow droughts, different snow drought types, and if there are any existing prediction products on subseasonal to seasonal timescale that user can use.
Yeah, I don't think there's a whole lot out there available in terms of products specifically for snow drought. And that's why I mentioned, temperature and precipitation are commonly predicted at subseasonal to seasonal timescales. Snow water equivalent is very challenging to predict. I think our climate models do output snow water equivalent as a variable, and so it could be interesting to try to get a sense of what some of these snow drought predictions look like. But I think there needs to be a lot more work there. I don't think we fully understand the predictability of these events. Some of the work on the spring heat waves is one example of starting to understand predictability of one aspect of snow drought, but I don't think there's been much work done on kind of atmospheric circulation patterns early and midwinter related to these various types of snow drought. And so again, I think it's an area that's ripe for more work.
Okay, thanks so much. So the last question, could you comment a little bit on the relationship between snow drought and wildfire in subsequent seasons, for example, in subsequent summer and fall? Are there any existing studies on this?
Yes, so there are studies out there linking snow-covered area and snow water equivalent to things like acres burned and fire severity and that sort of thing. But it gets complicated. As I mentioned, it's not a one-to-one relationship between snow drought, big wildfire season. I think this year is a good example when after all the snow melts out, you can shift back to cooler and somewhat wetter conditions. And then when that happens, you can also get more growth of vegetation and fuels like grasses that can actually further increase the fuel loads later in the summer. Or if you have really wet conditions in, say, April and May, you can actually dampen the impacts and have less fire danger due to those spring events. So I guess what I'm saying is the spring and even the summer weather, things like the monsoon, are all really important to fully know how the wildfire season is going to progress. But the snowpack is just one factor that I think shifts the odds towards more fire activity in the summer if you have a snow drought year.
Yeah, thanks so much, Dan. And thank you to our audience for your questions. And thanks so much again, Dan, for addressing these questions and for the wonderful presentation. So now back to you, Andy, to conclude this seminar.
Yeah, thank you so much. Thank you, Dan, for presenting today, and thank you all for attending the June 2026 edition of the NOAA Drought Seminar Series. The next seminar in this series will be on July 13th, 2026 at 1 p.m. Eastern Time with a presentation by Dr. Jeff Basara, Professor and Chair of the Environmental, Earth, and Atmospheric Sciences Department at the University of Massachusetts Lowell. Jeff will present on flash drought monitoring mechanisms and predictability. You can register through the link in the chat or via NOAA Drought Seminar Series webpage. Again, we welcome your feedback. Once the webinar ends, a short survey will appear where you can give feedback on this seminar and the seminar series as a whole. You can also reach us by email that's shown on the screen. Once again, thank you very much for attending, and we hope to see you all again next month. Goodbye.